Okay, so in this video I wanted to talk about forming primary structures when we have both internal and external redundants, i.e. internal basic forces and external reactions as redundants. Okay, so for structural models that are externally indeterminate, where we have more reactions than what's required for global equilibrium, we can, if we want to, use external reactions as redundants when we form our primary structure. So we'll show the equilibrium equations for this case and then apply the PVF in order to verify that an analysis satisfies a boundary condition. Okay, so in previous lectures on the PVF, we looked at how to form the equilibrium equations and then compute displacements at unconstrained degrees of freedom. But here we'll look at how to verify boundary conditions at a constrained degree of freedom. Okay, so here in equation 1, we have our equilibrium equations when we have redundant reactions. And all we've done is combined the equilibrium equations at the constrained degrees of freedom or unconstrained degrees of freedom. So PF equals BF PB plus equivalent nodal loads PFW. And then PC, this is for the constrained degrees of freedom. Okay. So what we've done is split this equation into redundant reactions, let's say PCX, and then reactions that'll remain in the primary structure, PCI, and then split the corresponding rows of B sub C into BCX and BCI, and the corresponding rows of PCW into PCWX and PCWI. Okay, so just splitting those out, and then adding the equilibrium equations of the constrained degrees of freedom that we treat as redundants, i.e. the subscript x, adding those to the set of unconstrained degrees of freedom, or equilibrium equations, P sub f, BF, PB plus PFW. Okay, so everything above this line within the equations. Okay? All right, so again, just taking the equations and moving things around. We haven't really changed anything, just moved our redundant reactions into the set of unconstrained degrees of freedom. Okay? Okay. So assuming that we didn't have enough reactions to reduce the indeterminacy down to 0, this matrix BF BCX, i.e. the one up here above the line, has more columns than rows. All right, so we still have an indeterminate system after releasing one of our reactions. Okay, so now on this we can use the RF command in order to find a stable and determinate primary structure, just as we did with the case of all internal basic forces as redundants. Okay, and basically what this does is it takes columns away from this equilibrium matrix in order to find a stable and determinate system. Okay, so when we do that, basically what we're doing is taking this matrix up here and then splitting the columns apart. Okay, so we end up with what remains in the primary structure and then what's part of the primary structure and then what's part of the redundants. And in doing so, we split the basic force vector into PBI and PBX. Okay, so kind of doing the same process we did for internal basic forces only, right? But we had this first step up in equation 1 where we move some of the external redundants into the unconstrained degrees of freedom. Okay, but basically this matrix in the upper left corner is going to be square and invertible. Okay, and this is the equilibrium solution for the primary structure. Okay, and that's really what we're after. Okay, so doing a little bit of algebra, all right, we can solve for PBI up here. All right, so we can take this this vector over to the other side, okay, and then invert this BFI, BCXI aggregated matrix in order to give us the solution for statics of the primary structure in terms of redundant basic forces and then whatever our applied loads are at the unconstrained degrees of freedom as well as the redundant reactions. Okay, the PF and the PCX. Okay. Again, I've skipped a few steps going from equation 2 to equation 3. All right, but all we're doing is just multiplying this out and then solving for PBI. This is all just statics. Remember when we have BFI inverse, that's really just code for do some statics. Okay. But once we know PBI, all right, from this, whatever our applied loads are, and our redundant basic forces, and then the redundant equivalent nodal loads, okay, we can solve for the reactions of the primary structure, okay, shown here in equation 4, okay. So in order to use the PVF, we use a virtual form of equation 3, which is right up here, okay. And since we're dealing with the PVF, we can assume that there's no member loads, all right, so PFW and PCW all go to 0. We throw deltas in front of everything to indicate virtual, and we end up with the following equation 5 for the solution for the internal basic forces in our virtual force system. Okay, so it's just equation 3, but with the member loads taken out. But again, this is arbitrary, all right, and these are arbitrary. Okay, and then all these inverse matrices here are just, again, code for do statics. And this delta PBX is usually going to be 0. All right, so this whole term will go away, this term right here, okay, when we do the PVF, okay? Okay. So then playing kind of the same tricks as before with the case where we have only redundant internal basic forces, all right, we can get the following solution for the for all the basic forces by adding this identity delta PBX and then writing it simultaneously with our equation 5 for delta PBI. Okay, and like I wrote here in the notes, this is not as bad as it appears. All right, the size of the 0 matrix and the identity depend on how many external reactions are used as redundants. For most practical applications, we'll just use one external reaction when we're verifying boundary conditions. Okay, but after we solve equation 6, all right, then we can go back and recover the reactions of the primary structure with delta PBI and delta PBX known. Okay, and I'll show you how this looks like a lot of linear algebra, and it is, but I'll show you here some of the basic steps to apply these equations, and then in a separate video in Python I'll show you an example. Okay, so say we wanted to verify a known boundary condition. All right, we'll use the PVF to do that. All right, so this is our statement of the PVF down here, external work equals internal work. Okay, the general procedure for going through this calculation is shown here. Okay, I won't read through it, but you can look at it at your leisure, right? Leisure. Okay, but suppose we wanted to verify that these element deformations for our structural model we've been looking at, that these element deformations satisfy compatibility, or that a boundary condition is satisfied. Okay, this is element 1, element 2, element 3, element 4, and then this little spring is element 5. Okay, so this is partitioned off like this. This is 1, 2, 3, 4, 5 elements. 1, 2, and 3 are our frame elements, so there's 3 basic deformations. 4 and 5 each have 1 deformation for the truss and the spring. Okay, these are the global degrees of freedom over here on the right. Okay, so there's 8 unconstrained degrees of freedom and 5 constrained degrees of freedom. All right, and what we want to do is verify that this analysis, whatever analysis led to these basic deformations up here, that it satisfies the vertical boundary condition at the pin support of the frame, okay, i.e. constrained degree of freedom -2, or this one right here. We want to make sure that that boundary condition, which is 0 displacement, at and in the direction of degree of freedom -2, is in fact satisfied. Okay, so following the steps that were shown above, we first move the second row of B sub C into B sub F. All right, and this is some Python code to do that, assuming that you have BF and BC already defined. Okay, but I'm defining an index vector here for which row we're going to move out of BC. Okay, so remember that Python has a -1, or the indices start at 0, right? So the second row would be an index of 1, first row would be an index of 0. Okay, and then this, so CX tells us which reaction to use as a redundant. CI is just the set diff of the remaining NCDOF. I'm just splitting out I and X, and then we use VStack to add the rows of B sub C contained in CX, or indicated by CX, onto the bottom of B sub F. All right, and then, so we have BF new, and then we also have BC new, which is just the remaining rows of B sub C. So we're pulling out the second row, and then forming some new equilibrium matrices. BF got 1 row bigger, BC got 1 row smaller. Okay, as shown down here. Sorry about the zooming here. Okay, but here's BF and BCX. All right, so there's 8 rows up here and 1 row down there. Okay, this is NFDOF plus 1 for the redundant reaction. Okay, so basically what we've done is make the structure 1 lower indeterminacy by changing the pin into a vertical roller, which is shown right here. So we've gone from this to this by quote-unquote releasing the second reaction. Okay, after releasing it, we can now make the structure determinate by using RF to find 2 redundant basic forces. All right, we can use the SymPy package in Python to do that. Okay, shown here. We SymPy matrix BF new, RF, and then JI is the index vector of the basic forces that remain in the primary structure. Okay, and that comes out as 0, 1, 2, 3, 4, 5, 6, 7, 8. All right, so the first 9 basic forces remain in the primary structure. Basic force 10, which was from the truss, is a redundant, so that goes to 0. And basic force 11, which was this rotational spring down here, also goes to 0. And we end up with this primary structure over here. All right, so it helps to kind of see this transformation from our original structure right here to our primary structure, which should be statically determinate and stable. Okay. Then we can start applying virtual loads onto the primary structure. Okay. So, to this end, all right, we have dPF, dPCX. All right. So this is of length NFDOF plus 1. Okay. That's all zeros at the unconstrained degree of freedom, or degrees of freedom, and then a 1 at and in the direction of the redundant. All right, so what do we have? A vertical roller here, and then basically a pin there. So what we're doing is applying a 1 at the release. Okay, And we're going to compute that displacement and then make sure it's 0. All right, if that's 0, we know that the boundary condition is satisfied. Okay, so then we can go through and do statics, mathematically representing equation 6, but in Python we can use NP len alg solve with our new equilibrium matrix, BF new I, and then our load vector, which was this one right here, okay, to get all the basic forces. Okay, dpbx is all zeros of length dsi minus 1. Okay, then we can stack everything together, and we have our basic forces for our 3 frame elements, and then our truss element and our spring element. 1, 2, 3, 4, 5. Element 1, 2, 3, 4, 5. Okay. Then we can use statics to find the reactions of the primary structure using equation 7, and here's the Python code to do that. So this np dot dot does the matrix vector multiply for the basic forces of the primary structure, and then matrix vector multiply for the basic forces of the redundants. All right, this is 0. I didn't need to type this, but I'm just doing it for completeness. Okay. And then that vector works out to -5, 1, 5, -1, 0. So these are the reactions of the primary structure. Okay. So this, once we have, I'll just go through the math real quick and then show you what the equilibrium looks like, and then we'll be done. All right, but we have everything we need to evaluate the PVF. All right, we have dP B transpose U sub B, and then we have delta PC transpose U sub C. Okay. On the right hand side we have delta PF UF, okay, minus that. Okay, we're trying to solve for the entry of this vector that corresponds to our constrained degree of freedom. So after you do this, these inner products, you'll find that you get 0. All right, which means that in fact the analysis does satisfy the boundary condition, because the boundary condition says there's no displacement at a direction of constrained degree of freedom 2. Okay, and all the math shows that. Okay. So what I want to do is on the exploded free body diagram show you these basic forces right here in this vector, as well as the reactions of the primary structure, shown right here. Okay. And that's shown down here. All right. So we had, although I'm showing all the original boundary conditions, but basically we have a 1 applied here. All right, this is released. So that's a roller. Okay. Our basic forces for this element were -1, 0, 60. All right, so we have 1 here, 0 there, 60 there. Okay. And then for this element we have basic force vector of 5, -60, and 80. So 5, -60, and 80. Okay. And then down here for this element we had 1, 0, -80. All right, so I think that's 1. This is 0, -80, going that way. Okay. And then 0, 0. All right, these were redundant, so of course they're 0. Okay, let me get rid of some of this stray marks. And that's 0. Okay, so those are all the basic forces, and then the reactions, which again were shown up above, but we had -5 for constrained degree of freedom 1, so we had 5 going this way. Okay. Constrained degree of freedom 2 was 1, which is what we applied. Constrained degree of freedom 3, which was over here. This is 5, and then we get -1 there, and then this is 0. Okay, so this should all satisfy equilibrium. You can at least see that the moments balance out, right? 80, 80 equal and opposite, 60, 60 equal and opposite. Okay, and then 0 for the roller down here, 0, 0, 0 down through here with the basic force from the spring. Right, but I'm not showing all the reactions of the basic systems, but you can do that. But the figure will get pretty crowded. Okay. All right, so there's some other videos on Canvas showing how to do the Jupyter Notebook for these types of calculations. And thank you for watching.